Good morning, GMGM. Thank you, everybody here, for choosing to spend your time at our third inaugural NoirCon.
The goal here is to take you through how you might actually start to utilize some of Noir's more advanced type features. Noir is a very expressive language, and a lot of times when people think of ZK DSLs, you might think of something that is more low level. You have to be, as you know, one of Noir's goals is to be as developer friendly as possible. But I want to take you through like a narrative of what we actually might want to build. So as you might know, ZK Passport is a project that's now in production. And what is ZK Passport actually trying to do, and how does it keep your identity private from third parties? So in modern passports, we have this chip, RFID chip, that basically has your personal information. And that's what actually like the government is going to scan when it's trying to verify that you have a valid passport. And then once you actually have the ability to prove that you contain a digital signature, that is actually, it gives you the ability to prove personal information. The goal is to verify this signature in a ZK circuit using a language such as Noir. However, the issue is that every country, like once you start to want to actually apply things in production, you realize there's a lot of edge cases. Every country has its own cryptography. They use their own cryptographic curve. I've listed a few here, but there are many, many more. You can probably talk to the ZK Passport guys about how many different curves there are, and different bit sizes and different fields. The issue is Noir's native field right now, the one that we support natively, is 254 bits. Well, I've listed a few that are bigger, but there's many that are bigger. So yes, as I just kind of went into, not just in ZK Passport, but in general, lots of different cryptographic systems in the real world use larger scalar fields. So we have to then ask the question, how would I actually verify a signature on one of these curves in a zero-knowledge circuit? Basically need some way to represent our number in larger than 254 bits. So this is what we wish we could do. The field type is what's native to Noir. I wish we could just have a public key X, public key Y, R, S, message hash, and then we just easy. It would be really nice. I have a repo. I don't expect you guys to code along, but it's been broken up into stages that might make it easier for you to follow along. And then in the presentation, I'll be going through the different segments. But the repo has also more content that I think would be useful for after the talk. So let's get started on building basically a big number. So I want to verify on the brain pool P384 curve. So we'll start with this simple structure, just 4 different limbs. So we're trying to represent in Noir something that's bigger than 254 bits. Here's this is kind of a very simplified version of how we might construct it. And everything's in big endian. You can, of course, look into the repo to, if you want to explore it more, because I'm going to probably be going through these methods decently quickly. But in general, the idea is we want to take in a byte array, and we want to convert it into our type structure. We can then test it in Noir. You can easily use nargo test, as you would expect with something like Rust, using cargo test. We can add our arithmetic operations. This is not how you would implement it in production. You have to propagate your carries across limbs for accuracy. But this presentation, I know it said a production-ready library, but this is to show off the type system of Noir and the features there rather than the arithmetic correctness. We can then test that method as well. And you can see I created a 5 big number, 3 big number. We've added them together, and our last limb is 8. Multiplication, it's a little bit more complicated. Once again, this is still a simplified version. We're basically trying to multiply in little endian, which is a little bit easier to reason about, and then we're going to switch back to big endian, back into our actual format, our type structure that we have. This is, yeah, you can see noted here that there's a lot of different things that are not actually properly handled. And then, of course, we can check that as well. And here we're just doing a 6 times 7 equals 42. So we go back to what we wish we could do. Now we have, for our public key x and our public key y, we have a structure for our FQ that maybe we can use and start doing the actual arithmetic operations on that we want. But R and S in the verification algorithm, they need a different field. FQ is the base field of our curve, but we also need the scalar field to actually verify our signature, which we refer to as FR. So this is what we actually want to get to. Show it so we want to be able to construct an FQ and an FR. So let's construct our FR. Once again, it looks very similar. This one, at least, is just 4 limbs. Actually, the structure is the exact same. You can notice in the last bullet point, though, this is a finite field, though. They do have different moduli. So when you they do behave differently in practice. And when you saw the multiplication earlier, one of the notes is that you need to have a modular reduction, where you basically modulo every arithmetic operation you're doing. We're kind of hand-waving that for now. But let's start to generalize our structure. So we can create a big num. In Noir, we have generics and we have numeric generics. So you can see here how I have both a limbs, so that is used to specify, okay, how many limbs do I want? And then a params. This is where I'm just kind of hand-waving the modulus a little bit. And you can just assume that there's field-specific information in there. So now we can make a generic structure. So we still only accept a byte array of 48 limbs, but we're using our numeric generics limbs. This would live inside of the type implementation. So if you're thinking from Rust, we have impl FQ. This lives in there, so we can access that numeric generic. Same thing. You can see the limbs. We're iterating over them like this. And then the same thing for multiplication. So now we want to distinguish their parameters. We have the ability to specify traits in Noir. If you're unfamiliar with traits, a trait is essentially just an interface that defines several methods. And types will provide their own implementations of these methods. So for our FQ, we have this implementation of the modulus. This is the modulus for FQ. And then for FR, this is the modulus for FR. They're very similar here, but the first limb you'll see is actually, I'll just go back. You can see the D3A and then 3AB. So we do have a different implementation for this modulus function. And then now we can specify 2 different types using type aliases, which is also something that's supported in Noir. So now we have an FQ and an FR. Oh, okay. Based off of this big num structure. And now we can use it in tests as well, that type alias, just as we would have used our big num structure. And this is the switching to it. Well, the thing is, we have now created this structure, but we want to have some generic interface for our big num. And here, this is the aware constraint for our trait. So we basically said FQ and FR must be a big num interface. So before we had a structure where you can't just do that here. You need some kind of interface, which is the traits that I referred to earlier, but we were using it for the parameters. So now we're going to construct a big num trait. So every big number is expected to implement this trait. And you can see I have a simplified interface here where we just have a constructor, and add mul, and then now we actually have the params is returned directly from this big num trait. This is what we were specifying in our where constraint in the earlier slide. So for each of the structures now, you have to implement your trait. So I'm going to leave out the implementation now because you've seen it enough times, but you now have for FQ and FR, we've implemented these methods. And same thing here. We have the ability, though, in Noir to take advantage of operator overloading as well. And this is something very nice when you start working with our trait interfaces. So you can see it from our old test. We do a.add b. It would be really nice to not have to do that, though. So this is operator overloading lets us define operations over like different, more custom types. So we can implement traits such as EQ, add, mul, and these operators will then become available to those types. So now in our big num trait, we'll specify that it has what we call, like we can essentially inherit the other traits like add, mul, EQ. It's technically referred to as a parent trait. So when I have my big num impl like this, if I don't implement one of these parent traits, I'm going to get this error here. And you'll see it's telling me that I've not satisfied a certain trait constraint, which is our, in this case, add. So now I can make a trait implementation for my FQ big number. And this looks the same as what we previously had. But now in my test, I can just do a plus b, which can improve our user experience a lot more. And also at the end, you'll see I'm using the EQ operator as well. However, the thing is, each implementation we don't want to have to do that for every big number. There's a lot, like I said, every system has every country, for every passport, has tons of cryptographic curves, tons of cryptographic numbers. Do I want to make the same boilerplate every single time for every single function? No, you don't. So how can we reduce this? And Noir supports basically compile time metaprogramming to make this a lot easier. It lets us generate repetitive code in Noir, so we can code Noir code in Noir, and we want to be able to make a macro that can have a type. So our structure, so FQ or FR would be our type. It accepts some parameters like the number of limbs or the actual big number parameters. And then we should automatically generate basically everything. And we want to then be able to specify a big number with just a single call to a macro. So I'm going to quickly, before we get into that, describe how Noir's metaprogramming works. And there's two concepts, really. We have comp time, so the comp time keyword you see there. This means everything is executed at compile time. And then the quoted and unquoting. Quoting is essentially just we are taking a string of tokens, basically parse this code as just raw as you would any Noir code. So we're just injecting Noir code into Noir code. So in this case, we have quote 1. So this just literally just 1. And then we can unquote using the exclamation point. If you're familiar with Rust macros, this is how you invoke a Rust macro. If you've ever seen like print line exclamation point, it's a call to a Rust macro. So here we're doing an unquote. So that B is at compile time is going to just be B equals 1. It reads like as it does here when you're writing your Noir program, but that's actually what it's going to be. And then we can use it inside of our Noir code. So here we're just doing a simple as, we're just casting it into a different value. To give a little bit more an example, you can also unquote inside of your quote. So here we have an x that is just 1 plus 2, but it's not. I want to be clear. Like 1 plus 2 is not being evaluated. Like it is just 1 plus 2 as written in code as you see it right there. So y is actually just going to be 1 plus 2 plus 4, and then that's what will be evaluated. So let's do that for big num. We do have some extra compile time specific types. So you can see type definition refers to a structure. So this means we're accepting some struct. We're accepting a U32, and then we're accepting a quoted. So something that is quote, and there's something inside those quote brackets. And we're returning a quoted as well. And obviously the goal here is, like as I said earlier, we want the big number, add, mul, EQ. So here let's get into how we can do our metaprogramming. So we have our implement big num trait. Big num is already, it's in our crate here. We're accessing it through a path, and we're calling that unquote $ operator. So we're saying, I want to implement big num as it is written there for this given type. So if I was to think about the implementation we had earlier, this would just read implement big num for brain pool P384 FQ. And then we also have some helper functions where now we just purely operate over the limbs. And then you can also see how we've also implemented the params function. And that's just returning the parameters that were supplied here. Does that make sense? Any questions on this one? Or should we just move forward? Or maybe I should wait till at the end we do questions. All right. I said how we have this generic limbs function now. This looks very similar to the function we originally had when we just had our generic big number struct, but now it's just a standalone function. And now we can also do the same thing for our type implementation. So we have our standard lib imp, impl, and then for that given type. And once again, we have a generic or generalized add limbs method. Add limbs, once again, looks like we saw earlier. We can do it for all our types now, or all our trait implementations now. And this is how we now have our metaprogramming specified for each impl. And now, when it comes time to specify a custom big int type, I can call that macro in an attribute on top of my structure. So you can invoke a macro like this on top of a type, and it's going to basically immediately unquote. So that's what I mean by bringing that token stream back into Noir. So the first thing that will be passed to derive big num is going to be the type itself. You see FQ and FR. That was the first parameter of our macro. It's going to be passed into that function. And then they're both for limbs, and we have some certain params that we've specified earlier that I showed you where it was just a structure with a certain modulus. I'm using a structure because in like a production big number, you're going to have a few other parameters, and it's better to just use a structure because you might be able to extend it more in the future, or just extend it more easily. And that's how we then invoke our macros. I just want to highlight, though, that in our production big number, even though there's all this abstraction, all this kind of what looks like should slow down the code, it is still quite efficient. This is in ultraplonk and ultrahonk, although ultraplonk, I don't believe Berettenberg supports at all anymore, so the only one that's really relevant is the 2 columns on the right there. 100 multiplications with a 2000-bit big num, you can see is 1.4 seconds. This is in milliseconds here. And then additions, 400 milliseconds. This is usually more operations than you need for most applications, so it's still quite fast. And the ZK Passport, like actually generating a ZK Passport proof, which does a lot more, it's doing like curve operations, which use this big num as a dependency, occurs in about a minute, which it's been a lot of work to get to that time. I want to credit ZK Passport though. If you guys should check out their circuits where you can see how they actually use this in production. I'm going to give a second for people to scan. And I want you guys to, take a look. Here's a link to the docs and also my X. And you can, if you have questions, tweet at me or go on GitHub, file an issue. Someone at the team will be happy to respond. And yeah, I'm happy to take questions now. And I can go back in the slides too as needed and stuff. I'm not sure who's handing out microphones, but we're ready for questions. Yeah. It would be very unlikely to upstream that into Rust. Rust has a whole process for their process, and Noir is not actually dependent on Rust in that way. The compiler is built with Rust, but this is Noir's unique metaprogramming. We found Rust's metaprogramming to be inefficient and insufficient for our needs. I actually find our be a bit easier to work with. So yeah, no, it would not be upstreamed into Rust. The comp time keyword is much more similar to something like Zig, if you're familiar with Zig. Although ours is, I'd say, a bit more flexible, which has trade-offs though.
Yeah, I was gonna ask about that because there is a way to do compile time functions in Rust, which is the const keyword. So I was wondering why the comp time keyword. I don't use Zig, so I wouldn't know. But yeah, const functions are a thing in Rust, and I believe it should be the same thing, or is there any difference?
I am familiar with the const keyword in Rust, but I am not familiar with this, that they have some advanced compile time interface of I'm not aware of that. Maybe we can discuss it after, but in general, we are closely modeled after Rust and their syntax, but we are not, it's still a distinct language. And so we felt the comp time keyword was clearer that this is occurring at comp time. Everything is a value. It's not only, it's not just a constant that exists. It is in Rust, you can specify, I know, we have a constant, and but that might be a global constant that you can call to in a method. Here, everything is also evaluated at compile time. Everything in comp time is evaluated at compile time too. That might be a distinction, but we are not going to be always kind of following Rust exactly, even though it might be very Rust-like, the syntax.
Yeah, when you do a const function, it's the same thing as a compile time function. Yeah.
Okay. Well, either way, it's still just a keyword because we could just have const. I find comp time to be a clearer keyword.
Yeah, thanks. I'm trying to run the workshop demo, but it looks like it's not similar as the slides. So
there's more information in the workshop demo. Because I'm just took splices from here. But if you run nargo test, it should all run. If not, please file an issue. I'll fix it.
Would you like to run now or later?
Well, if you go, so I tried to put it into stages. Master on that repo is not going to be what you need to look at. There should be, if you go to the pull requests, sorry, I should have specified that. And the branches, we have a stage 0, stage 1. Stage 0 is just the very simple big num. Stage 1 then should be our generic big num that is it gonna, I guess we're, okay. Stage 1 is our generic big num that I showed originally, and then stage 2 is gonna be, we actually implemented a big num trait, and then stage 3 will be using metaprogramming to get rid of that boilerplate. So yeah, I wanted to try and split it up so you could see the progression from the initial just very simple big num. Does that help? Any other questions? They can be about, they don't necessarily have to be about the presentation. All right. Sweet. Thank you for listening. Happy everyone's here. And I'll be at the booth there if anyone has questions you don't want to ask right now, you just want to ask it privately. All right. Thank you guys.